Hello, everybody. Recording is started. So there should be Group B Challenge 0 that still has to present, correct? Is Group B Challenge 0 here? Group B Challenge 0? You guys are here?
Yes, we are here.
Okay, perfect. So again, apologies from last time. Yeah. First weeks, it's a little bit of a mess. Go ahead. And today also we have the movie review. Don't forget, guys. So we also have the movie review because I recognize the style of the PPT. I know. Go ahead.
Hello, we are Goofy. Today we will be presenting our analysis for Challenge Zero.
So your microphone is a little bit. The quality of your microphone is a little bit crap. Can you try to do something? Can you check your microphone? It looks very broken. Otherwise, we just turn on the captions.
Hello.
Okay. Your microphone is a little bit crap. Go ahead. We'll live with it. No worries.
Oh, let's take a quick look at today's roadmap. We'll begin at level 1 by laying out the basics of our data set and its general statistics. From there, we will set it up to compare drum rate, artist, and danceability across level 1 and 2. And to wrap up, we'll go into a level 3 deep dive, exploring how different features will relate and analyzing the overall user space to blockchain. And for level 1, the assignment asks us to plot a histogram of track probability and find the average score and determine whether most songs are obscure or popular. Look at the histogram on the left, and you can clearly see the distribution. There's a massive spike right at the 0 to 10 range, which contains over 20,000 tracks.
Yeah.
And as the popularity score increases, the number of the tracks generally drops. This visually trend immediately tell us that most songs on the platform are quite obscure. And to back this up, and let's look at the summary statistics table.
Yeah, I think that's a statistic, right? I think that what is it, like 20% of the songs on Spotify have 0 listens. That's why you have this spike at 0, right? Because people upload songs and then people never listen to them. So the popularity is 0. Yeah, it's something that you expect. Go ahead.
And out of these tracks, the examined popularity is only 33.24. Furthermore, the table shows that the 15th percentile is exactly 50. This means that the 75% of the songs in this dataset score 50 or below. Both the visual chart and the statistical data perfectly align to prove that highly popular songs are actually very rare. This slide answers the level 1 requirement to explore the distribution of audio features using histograms. The stability was a bell-like curve peaking around 0.6. So most songs are moderately danceable. And second, every energy strongly leans to the right, indicating that the vast majority of tracks are high energy. Balance, which represents musical positivity, is widely spread out but slightly concentrated in the lower middle range. And finally, tempo is heavily clustered between 100 and 150 beats per minute. From this, we can conclude that a typical Spotify track tends to be highly energetic and reasonably fast,
Mhm.
but its emotional sensitivity varies quite a bit. And this slide answers the level one requirement to visualize the top 10 genres by the number of tracks.
Yeah, so this is how they engineered
And
the
the,
data set, right? That's how they engineered the data set. Go ahead.
the chart, the chart reveals a very interesting and unusual phenomenon. The bars are perfectly
No,
level.
it's not unusual.
Every
It's not unusual.
single
It's not unusual. That's how they engineered the data set, right? Because they when they did the data set, they balance the data set over the genre, right? So basically, you can imagine that when you have to release the data set, right? You want the data to be uniform in some sense, and they chose the data set to be uniform in terms of this, right? So they sampled 1,000 songs for each genre. So go ahead.
every single genre strong tier contains exactly a thousand tracks.
Yes,
From
yes,
this, we can conclude that this database doesn't reflect a natural real-world distribution.
correct,
Instead, it was artificially balanced by the creators
correct.
who intentionally sample exactly 1,000 songs for each genre. Hmm. Uh, this slide addresses the level one requirement to produce backlogs of audio features, specifically showing the ability groups by the top five genres. And looking at the results, we can observe some distinct patterns. Afrobeat clearly stands out of uh, the highest median score, showing it's consistently the most danceable genre among the five. On the side, ambient music has the lowest median danceability. However, ambient also displays the widest vertical spread, meaning its rhythm and beat vary drastically from track to track. Meanwhile, acoustic, old rock, and alternative are clustered in the middle, sharing very small, similar median scores of around 0.5855.
Very good.
And you can also spot a few low scoring outliers represented by the little circles at the bottom.
And those are the outliers. As we did discuss it last time. Yeah, I imagine what ambient music is very danceable, right? So some dripping of water or some waterfall music, probably it's very danceable, right? So go ahead.
And this slide answers the level one requirement to explore artist activity by plotting tracks counts and identifying the most prolific artists. And looking at the histogram on the left, we can see a heavy rise to distribution. The massive first bar indicates that the vast majority of artists only have one or two tracks in this dataset. Conversely, the table on the right highlights the extreme outlier. The Beatles ranked number one with an impressive 239 tracks, closely followed by George Jones at 271. The list also includes legends like Steve Wonder and Ella Fitzgerald. as well as modern bands like Linkin Park, all contributing around 200 tracks each.
Which one is your favorite here in this list? Which one is your favorite?
Uh, the Beatles.
The Beatles? You prefer the Beatles over Linkin Park? Really? Very good.
Was only for the songs.
But you never listened to Linkin Park, really?
Yeah.
Jesus, they just came back with a new song with a female singer. Go listen to some Linkin Park. I mean, it's good music. I understand if the other ones they're too old for you, but Linkin Park they're still active today, right? The Beatles have been gone for a while. Gosh, the young people, you know. Go ahead.
Okay. This correlation limit attributes our final level one requirement. To read it, simply look at the color scale on the right. And dark red means a strong positive correlation, and deep blue means a strong negative correlation. And light colors means no relationship. For instance, look at the chart. We see a strong negative correlation in deep blue between energy and acoustic. Acoustic mix. Conversely, energy and loudness show a strong positive correlation in dark orange. However, the most important takeaway is the popularity role and the very top. It consists it consists entirely of light, nature, and neutral colors. This reveals a key insight. No single audio feature, whether it's tempo, sensitivity, or energy, can strongly predict or guarantee a song's popularity. And next one.
From now on, we'll focus some analysis with track and time. First of all, let's look at this line chart showing the number of track released per year. This graph captures the macro evolution of the music industry over the past 5 decades. As you can see, from 1970 until roughly 2010, the trend was relatively flat. The number of new music releases was stable and growing slowly. This was the era of physical media, like CDs or some
That's a good point.
where production and distribution were tightly controlled by major record labels. However, look at what happens after 2010. We see a massive, almost exponential explosion in music production, peaking dramatically in the early 2020s. This curve illustrates the digital music revolution, the rise of global streaming platforms like Spotify, combined with the accessibility of affordable digital recording software, completely democratized music production. It empowered millions of independent artists to create and distribute their music without needing a traditional label. We are now living in an era of unprecedented music choice. Next page.
Wait a second. Because I was checking, right, while we were talking. So Spotify opened in 2008, and Apple Music was launched in 2015. So I'm trying to understand, trying to figure out what is the peak there around, what is it? Probably 2000. Yeah, that's, you see that there is a peak around what, 2000, 2008. That probably would be Apple Music. I don't know. Yeah, can you see that peak there?
Yes.
I wonder what is the peak. Because when it goes down after, let's say, 2025, it's just because the statistics they're not fully complete for their year, right? So they just probably
Yes.
release around March or whatever. There is some music missing, but I try to understand what is the peak there. The peak around whatever 2015. I wonder if it's Apple Music. Yeah.
Maybe Apple Music. I use Apple Music, so maybe it's Apple Music.
Because you use Apple Music, so yeah. And now I think if you keep going there, now the spike is to the moon, right? Because now people upload all these AI songs, and now the artists that you said were empowered by the digital platform, they're actually drowned out by the AI music. It's a very sad story. Anyway, so do you use Spotify personally? Do you use Apple Music?
I use Apple Music.
Yeah, because do Apple Music allow for AI songs? I think no, right?
They have pretty.
No, they
They
allow.
have many songs.
Yeah,
Yeah.
they allow AI generated songs on the platform, but it's implementing voluntarily. But implements a voluntary transparency tag to identify them. Starting March 2026, the distributors can label if AI was used for a material portion of the track audio, composition, artwork, or music video. Okay, interesting. Okay, go ahead.
Next page, please.
By the way, you have a much better microphone than your previous colleague, so I think you should suggest your microphone to your previous colleague. Go ahead.
Oh, okay. Okay. Let's transition from analyzing. Wait a second. Analyzing where music is produced and to when it was released, and specifically how release year that currently assign popularity scores. Next is make the list line chart averaging popularity over time. This graph holds a crucial key to understanding the Spotify data set structure. Again, the x-axis is year from 1970 to today. The y-axis represents Spotify current popularity score, average score on track from the specific year. Look at the tracks released in the early mid 1970s. Their average popularity scores are exceptionally high, peaking around 1976 at an average score of nearly 40. This is the highest point on the entire chart. However, look at the dramatic collapse immediately following the peak from 1976 to 1980. The average popularity crashes down to roughly 15. From 1980 onwards, the graph enters a relative low valley plateau. Average popularity mostly bounces between 10 to 20. We see minor recoveries around year 2000 and 2020, but it never comes close to challenging the 1970s peak.
Yeah, I wonder. Yeah, I wonder who is that peak, because maybe I wonder. So survivor bias for sure is there. I wonder if they also changed the way in which popularity was evaluated, right? Because I don't know. So is popularity only calculated using their own listen statistics? So they see how long. You know what I mean? Because popularity, there is also some outside charts, right? So the Billboard 100, whatever. I wonder if maybe they changed the scoring of these older songs, that they also took, let's say, the positioning chart in understanding the popularity. I think it's not a straight up formula where they just take the number of listens. They probably also put some chart information. I wonder. Do you know how it's calculated, popularity?
Actually, I that's like the popularity.
Sorry.
Maybe.
Go ahead.
I don't know.
Okay. Yeah, just
maybe 1976. There are some timeless classic like the Queens or some famous bands, so their popularity is very high.
Of course. Yeah, I agree with you. The
And-
survival bias is there for sure because it's a very small
Yeah.
set of songs which are very, very popular. So of course, the popularity is crazy. Okay, go ahead.
And
Go ahead.
contrast with the 2010s and 2020s, as we established in our previous slide. Digitization caused an explosion in the volume of releases. As a result, the database now includes everything, every obscure indie track, every exponential album. Since most of the millions of modern tracks are unpopular, there are no score drags the overall average down.
Yeah.
Next page, please. Next page.
One of your colleagues is.
Okay.
No, don't scream at them, please. They
Uh,
were multitasking probably. Go ahead.
Now that we know the sheer volume of music is expanding, let's zoom in and analyze categorical differences between genres. We selected three contrasting genres, classical, hip hop, and pop, and used the volume plots to visualize their distribution. A volume plot, the wider or fatter a section is the more tracks fall into the specific range. First, we examine popularity on the left chart. Classical music is heavily button heavy, meaning most classical tracks have very low popularity scores on Spotify charts. Hip hop, conversely, has a fat middle section, indicating consistently strong popularity among modern listeners. The most the most finding is pop music. It has a unique shape which we call a bimodal distribution. This reveals a stark polarization. Modern pop tracks tend to be either obscure flops at the very bottom or massive mainstream hits at the top, which fewer tracks in the average middle ground.
Yeah, nice.
And now let's look at the right chart. Danceability. This perfectly validates musical institution with hard data. Classical is concentrated at the bottom. Pop sit comfortably in the middle, and hip hop undeniably dominates this metric, with its widest section concentrated at 0.8, proving it is designed for rhythm movement. Yeah. Okay, so next page.
Okay. Let's meet her and to let's answer a question. Does any single audio feature strongly correlate with the song's popularity? To instigate this, we plotted the popularity scores against distinct numeral audio features, including danceability, energy, valence, and tempo. As you can see in this scatter plot, the results are quite revealing, though perhaps not in the way one might expect if you look closely at the correlation coefficients. The R value above each plot and the red trend line, yes. You'll notice they are all incredible close to zero. For instance, the danceability sits at an R value of just 0.035, and the energy is essentially zero at 0.001. What this tells us is that there is no audio formula is the most important for his song. High energy or high valence doesn't automatically translate to high popularity. It suggests that a track's success on Spotify is likely driven by external factors rather than the raw mathematical audio features alone.
Very nice.
And next page. Next page.
Everybody's getting upset with the student in charge of the slides.
Next page. Oh, okay.
Finally, too many points. This is unreadable, right? So next time, subsample a little bit, right? Otherwise, it's just a messy cloud. Go ahead.
Okay. We apply a PCA. PCA can help us reduce this dimensionality down to just two principal components, PC1 and PC2. So we can actually visualize the building space on a 2D graph. Looking at this plot, we see a massive continuous cloud of data points. Instead of finding distinct, isolated island of songs, we see that musical landscape here is essentially one giant continuum. There are no stark, empty boundaries separating different types of tracks. This visual confirms that songs blend smoothly into one another across the spectrum of race, mood, and timbre.
Yeah.
Okay.
But,
Yeah.
Okay.
Okay, next page. Okay, the finals page that we apply K-mean cluster to segment the songs. We use 5K.
Okay, fine.
Okay, to segment the song space on purely on their audio features. Here you can see the same PCA space but partitioned into 5 distinct clusters, represented by the different colors. Because the underlying data is a single large cloud, the algorithm has essentially sliced this continuum into geometric regions. But we can see just while the algorithm successfully groups songs with mathematically similarities, because the border are somewhere arbitrary. A single cluster might be contain a mix of different genres that just happen to share similar tempos or energy levels. Maybe further analysis mapping our genre metadata back onto these specific color groupings will tell us if these boundaries align with how we actually categorize music, but we didn't know how to, or didn't to apply how to transfer this data, mapping this data to a more visible, visible.
Yes. So there was the suggestion from last time, right? So sometimes you have to drop the first few PCA components and just look at the next PCA components. So if you look at PCA 3, 4, you plot different combinations and you can see some clusters, right? Because PCA 1 and 2, they just capture, let's say, some average behavior. So maybe you have to dig a little bit deeper. Yeah. Go ahead.
Okay, then maybe this is the end of our presentation.
Oh, already? God, already?
What?
Already the end of the presentation, yeah. So who are the people in this page? Let's see who you recognize. Who do you recognize in this page? I just recognize 2 people. I don't know. Oh, Bolton. Oh, the one is Michael Bolton. Who is bottom right? Who is the classical director in the bottom right? Some Japanese. Yeah, can you tell me? Can you tell me who's in this page? Who did this slide? Who is the guy in the bottom right?
I don't know. This is I think it's a slide on Canva, and
No.
I don't really.
No. It's okay, let's use the AI. Do you know the other people in the slides? Tell me the other ones. So go back to the previous slide. Go back to the previous slide. So go back. So the top left is who's top left? Who is top left? Come on, guys. Somebody tell me who is top left. And I don't know the guy. Sakamoto. I see. The top right, I see. I didn't know the guy. So it's what did he do? Which lyrics? What did he do? Was a Japanese musician, composer, keyboardist, record producer. What did he do? So he did Debussy. Oh, interesting. Okay, I'll listen to something today for sure. In the 2010s. Okay. Okay, good. We also did a song for Ukraine. Very nice. Top right is a joke, right? Top right is Michael Bolton. Somebody put it in as a joke, right? Because when they close the malls in China, they always play the song from Michael Bolton, right? Yeah. Merry Christmas, Mr. Lawrence. Okay, okay, thank you, guys. Yeah, Coldplay. I think you guys don't listen to Coldplay anymore, right? But, okay, good. Very good, very good. Okay, I learned something today. Okay, okay, I have to check out this. I have to check out this movie. So this Sakamoto was also an actor in this movie. Very good. Prisoner of War in Java. I have to watch that movie. God damn it. Okay, thank you for the suggestion, guys. Hey, with David Bowie. Yeah. How do you know these stories, guys? Jeez, I have to check it out. Thank you for telling me. Okay, I have to check out this movie. So it looks very good. Looks very good. Thank you guys for sharing. Okay, I think I see that you guys teach me something important as well. Okay, so let's go through the other groups. So there is a new set of groups, right? So now I'm gonna ask you group A, B, C, and D, and you tell me how it's going. And after, very quickly, right? So just tell me if you talk, where you talk, blah blah blah, and then we go through the next challenge, and then we have the movie review. I think that's about it. So we all go to this one here. We have A, B, C, D, E, F. A, B, C, D, A, B, C, D, E, A, B, C, D, E. No, so now we have a group until F, right? A, B, C, D. Challenge 0, there is also group E, sorry. Is there a group E from challenge 0 that still have to present? Is there a group E from challenge 0? What do you guys, yeah, there should also be a group E from challenge 0, right? Guys? Right, guys, is there a group E challenge 0? Okay, I guess group E challenge 0, we lost it somehow. Okay, challenge 1, group A, tell me something. Group A, challenge 1, tell me something. Do you guys talk? Do you guys, is the leader coming up? Is the leader showing up? Okay, so no input from group A. Okay, group E, challenge 1. Guys, a bit quickly.
Okay, group B and leader of group B.
Okay, very good. Nice to meet
Group
you.
E. Group E. Yeah.
Oh, group E. Group what?
Yeah. Oh, E. Oh, you said B?
Okay, so you're group challenge 1, group E. You're in challenge 1, group E.
Yeah. Sorry.
Listen, ask me. Let me tell you if I'm stupid or we went group A and then we jumped to group E in your mind. Usually go to A to C, right? But anyway, group E. Tell me everything. Don't be nervous. Don't be nervous. Tell me everything. Yeah.
We only created a live group for the challenge. We haven't talk about more detail about the challenge. We just
because you do everything in 1 week, right? I give you 2 weeks to do a job. You use 1 week, and yeah, go ahead.
Okay.
What else? That's it.
And we didn't do anything else. We'll discuss it later after class, I think.
Guys, I mean, you have to. I understand that you can just take the challenge and do everything with ChatGPT, but if you dedicate so little time to the challenge, then you don't learn anything, right? I mean, you can do whatever you want, but anyway.
Okay.
Guys. Okay, is there a group B? Is there a group B? B like beach? Group B?
I'm leader from group B. Yes.
Okay, tell us something.
We also create a line group app.
Okay. So your connection is not good. Can you repeat, or maybe somebody else from Group B can tell me something? Try to repeat. Your connection is a little bit atrocious.
Okay. Can you hear me now?
Still pretty bad. I don't think it's me. Is there somebody else from Group B that can tell us what's happening?
Okay, maybe I can say we
Okay.
just also created a line group, and
Very
I think that's it. Haven't started yet.
Guys, geez, you're so predictable. You're so predictable. Why do you make your life? Anyway. Guys, this is. I don't want to be. Okay, I don't want to be an old man. You guys like to work everything, do everything last minute. That's how you live. That's your style. So what can I say? Group C. Somebody from Group C is going to tell me that they're already working on the challenge and they have some preliminary results. Group C, come talk to me.
We create our line group and we are trying to do the preliminary setup.
Okay, we are trying to do. Did you read the challenge?
Yes.
Very good. There's an improvement already on the other groups. Go ahead.
So like right now we are trying to maybe like the setup is 80% finished.
Okay. Yeah, try to work on the same code base, right? So that everybody's working on the same file. Okay, very good. Group D. Is Group D here? What is Group D gonna tell me?
Hi, hello.
Hello,
I don't know if my other group members are here, but we haven't even created a group chat yet, so I don't know.
So you're beyond the other groups because you don't even have the chat. Okay, very good.
I don't even have the chat yet, but yeah.
Okay, so yeah, so hopefully everybody's because the way we chose the people for group for this challenge should be based on the fact that they were active on the past challenge, right? So hopefully somebody's gonna get active. But if nobody gets active, let me know, okay? We as I said, so if there is some problem with the people answering, then and people are not active, then we just reorganize the groups. Okay, very good. The group one, so group D, I write one person active, no progress. Very good. Hopefully things are going to get better as we go on, and you guys are going to start be more proactive. Group F, is there a group F? How is group F going? No, there is no group F. Sorry, guys, I'm a little bit drunk. Group, we're good. So they just this thing that group E challenge 0. I don't know if what I missed. Challenge 0 group E. I don't know what happens. Okay, it doesn't matter. Okay, good. So let's look at the challenge together. I'll tell you what's in the challenge. So as you notice, I always use overleaf for the challenges because this is for scientific writing, right? So professors, when they write paper, usually they use this tool. So I'm just very used to use this tool. Okay, so so the first challenge will be it's on the design of. Actually, guys, let's take a 2 minutes break, okay? Before we do this, just 2 minutes. I'll see you back at 07. Just walk around, get some water, and then we get back to this, okay? 2 minutes. Yeah, if you have any question, let me know, guys, especially group B, let me know. And I was thinking that, yeah, we can watch this movie maybe for the movie club. Because this Merry Christmas, Mr. Lawrence, I see. We have to pick a volunteer for the movie club for next week. That's it. Any volunteer for the movie club? I hope you watched the movie for this week. It was really good. It's very touching. Okay, go ahead. Let's discuss this. Let me know if there is any volunteer for the movie club for next week. Otherwise, we have to pick somebody random. Good. So the first challenge is just on the architecture of a deep neural network, of a simple neural network. So just a few, like this challenge covers a few basics in terms of as we said, of the architecture of neural network on the basic design. So what you do is that you do classification over MNIST using a DNN. Very classical things, right? So that's whenever you learn deep neural networks, that's always the first exercise that you do. It's a very historical data set in a sense, right? So it's really what historically we should consider as the first exercise in training a deep neural network, right? Because yeah, it has a very significant historical meaning. So the data set is 60,000 images. Usually you split the data set into 70% training, 10% validation, 20% test set. The images are 28 by 28, which means that the process they usually do is they are 28 by 28 black and white images, which means that when you vectorize them, you have a 784 long vector. And the value of the vector, they are color intensities, right? So they are coded in unsigned integers of 8 bits, so between 0 and 255. And what we usually do is that we normalize them between 0 and 1, okay? Because you usually normalize features either to have a fixed range between 0 and 1, or to have, let's say, mean 1 and variance 1, or mean 0 and variance 1. These are the usual transformation that we do. And then we train using cross-entropy loss. So we fix the entropy to be like cross-entropy loss. And the optimizer that we use is stochastic gradient descent or Adam. You can choose a little bit which one goes. Then you choose the learning rate. Batch size is 64 or 128. Just stick to the same. And fix your epochs to be 10 to 20 epochs. Okay, so the training time for this should be less than a minute, let's say. Even if you use let's say, not the latest GPU from NVIDIA, the training time should be very quick. So that now the exercises in the following, the rest of the challenge will be to train many different networks. But the network is sufficiently slow that it shouldn't take you that long to do it. So this is important. So if you want to be able to reproduce the results, you have to fix the random seeds during the exercises, meaning that there are many random procedures that the network is performing. For example, during the batch size, like we randomly pick elements from the dataset for the stochastic gradient descent evaluation. So what you need to do is to always fix the seeds at the beginning of training, so that you know that whatever you observe in one simulation can be reproduced by others. Okay. Otherwise, let's say you see some phenomena, right? You see some, for example, some overfitting or some specific behavior of the loss function, and if you don't fix the random seed, then you have no way to reproduce in the numerical experiment. Okay. Because every time you run the simulation, then the computer will choose a different a subset of elements for calculating the gradients. It will choose a different set of random rotation for the images, and so on and so forth. So always remember to fix the random seed. And in the report, what you usually want to see is always report the validation accuracy and the test accuracy. Okay. So first exercise is very simple. So create a fixed neuron budget and experiment with different network designs. So let's say that you do a parametric network, and you can have a very shallow network where you have these 728 inputs, these 10 outputs, and you have just one layer in between, which is very long. Okay, or you could have a fixed 2-layer network, let's say with 1,000 and 1,000, or you can have a deep architecture. For example, you have in this case 4 different layers, or you can also have some bottleneck architecture. Okay, so let's say that you start from 800, you go down to 200, and you expand again, and you go down again. So you can have different type of architectures. Make these architectures parametered in K, so that then you can repeat the architecture, you can repeat the experiment for a different total budget of neurons. And then I want to see a plot like the one that we saw in the slides, right? Where you have number of neurons on the x-axis, accuracy on the y-axis, and you see how the different architecture perform across a different number of budget neurons. Okay? Any questions? No. Okay. First one is easy. Okay. Main result is this figure here, which I want to see, which architecture perform the best, blah blah blah, and I want to see this type of behaviors, right? This type of discussion, overfitting versus underfitting, stability in the training, and if there are some shape that perform well regardless of the number of neurons. Okay. Next one is data augmentation. Data augmentation is very, very important in the sense that quality data is very hard to come by. So you want to be able to squeeze as much information as possible out of your training data, and you do that by applying transformation to your data set that will correspond to some natural transformation that the data will undergo. For example, in this case, we are talking about the MNIST data set. So these are handwritten digits, and you're trying to recognize the digit. Okay. So of course, the orientation of the letter can change of, let's say, plus and minus 10 degrees, depending on how was the placement of the image when it was scanned. So it's clear that if you are training this model to go into a post office to recognize the addresses of people's letters, of people mails, it's clear that the way in which the letter comes in our scanning apparatus could have a rotation which is random. So it makes sense that we take the original data set, we apply this sort of reasonable transformation, so that we also teach the network to be resilient, right, to the experimental condition in which the network will be deployed. Okay, and this again, it's a way of augmenting the data, meaning that even if we collected 6,000 images, we can generate a random rotation to, let's say, get to 120,000 images, so that we sort of double the size of the data set. But what we are doing is teaching the network that there are a set of transformation that it should be resilient to. Okay, good. Which type of transformation do we have? As we said, rotation, okay, translation, scaling, and some sort of elastic distortion, and erasure, and maybe also noise. Okay, good. So the first ones corresponds to the first 3 or 4. The first 4 correspond to something that could happen, and the last 2, they are more noise. Okay, so you want to also be able to tolerate a set of noise, right? So it's possible that, for example, there is some speck or some dust, so it creates noise. Very good. So apply the transformation on the fly, and then you train the model from scratch, and then you see if you gain some robustness. Okay. So notice here that when you do this transformation, you only apply the augmentation to the training set, and then the test set remains clean. Okay. So in this case, you will be able to see not the resilience to noise, but how much information you're able to squeeze out of the training. Okay, so the setting that we are investigating now is this. It's not the robustness to noise, but how much information you can squeeze out of the data when you apply augmentation. Very good. Okay. Then the next task is to see that this classification task is not universal for all possible classes. So we said that the task that we're doing is classifying the number between 0 and 9 from hand written digits. Okay, so you can ask yourself, is classifying a 1 easier than classifying a 9? The answer is probably yes, right? Because the 1 is intuitively, right? The 1 is, we're just looking for a vertical element, right? Whether the 9, we have some more complex shape to classify. So you expect that if you train the network and then you go back and see what is the per digit error performance, then you will have a different error performance for each class. Okay, so this is task 2. So I want to see the accuracy per class and the error rate per class. So you can give me a confusion matrix and you can tell me which digit is misclassified as which other digits. We all know that the 9 and the 8 are very close. The 3 and the 8 are less close. And so there should be some intuitive interpretation of this. Very good. Next is to introduce data imbalance. Okay, so since intuitively, right? So since different classification tasks have a different complexity, okay, you wonder if you could be smart, right, and speed up the training of the neural network by using fewer elements of those classes which are easy to classify. For example, we saw that the 1 is easy to classify. When I train my data set, I don't keep, let's say, 10% of the data 1, 10% of the data 2, 10% of the data 3. But for example, I just take 5% of the data to be 1. Okay, what I'm doing is that I'm reducing the data set size so that training is quicker and I have better gradients because I have less data. I have less data to use for training. So the idea is that I will shape my data set so that I have more elements corresponding to the tasks that are more complex. Okay, you can imagine how you will be able to do this in different settings, but in the classification setting, it's easier to imagine. So you take the different classes and you have mild imbalance, moderate imbalance, and severe imbalance. So you reduce the number of data set entries for 1 of 50%, 20%, and 10%. Then you redo the training, right? And you evaluate again the per class accuracy. Okay. So you see if by shaping the data set, you can balance the per class accuracy, of course. Okay, because in a sense, if you go to a client and you tell the client, oh, I have a network and my network classifies the digit between 0 and 1, and my error rate on classifying the ones is 0%. So if there is a 1, I'm sure I'm going to classify it as a 1. But my error rate for 9 is 50%. So then you ask, I mean, would you want to buy this network? Of course, the answer is not, right? Because if you classify all the 1 correctly, but all the 9s are unreliable, you can still not operate your neural network, right? It's not that if your address is 1111, lane 1, house 1, apartment 1, then you always get the mail. But if you live in a house that there's a 9 in the address, then you never get the mail, right? It's not a satisfactory product to sell to people. So of course, you will want to know that you can balance the performance of the network. Okay, good. So do this. Per class accuracy should be nice. And then task 4 is the one that is the most difficult, and I'm telling you now. So if you, let's say, most of the previous classes, you're going to do a boring job. I mean, there's not going to be, you're going to discover something for yourself, but I'm not going to jump out of my chair if you show me something. But task 4, I want to see how you do it. The idea is as follows, right? So imagine, right, that you forget about the labels of which image it was, but instead you only have the label of whether 2 elements belong to the same class or they belong to a different class. Okay. Then what you can do is that you can train the network, right, to do the following. You take an input and you produce a digit, right? And then you take another input, you produce another output of the network. And then you calculate the loss based on whether the 2 elements were the same or the 2 elements were different. And then you backpropagate the loss over the 2 network, okay? And then when you do the weight update, you average the weight updates of the two networks that you have used. Okay, so you can teach the network to do a good job in producing a number, which we will call an embedding, that describes the image, and images that have the same label should end up with a similar embedding. And then after you have obtained this embedding, you do k-means clustering. Okay, and then you see if by doing k-means clustering you're able to recover what the digits were. Okay, so what is the point here, right? The point is that the label of whether the images were the same or were different is going to help you train these embeddings. Okay, and then you use an unsupervised learning approach to see whether the network is doing a good job in really producing features that put images that are similar and in the same neighborhood in the embedding space. Okay, so this one here is the one where I think I want to see the most originality. Okay, any questions? Any questions? Especially regarding the last part. That's why, guys, I don't want you guys to rush. You know, it's because like I always try to put some nice, interesting problem, and if you rush, then you don't have enough time to think about this stuff. Just a pity. I think it's just a pity. Okay, any questions on this? Any question? Very good. Okay, so if you have any questions, then we go to some presentation. Okay, so we do a little in-class presentation, and we go on from where we stopped last time. Let me just slides. So we do optimizers, and then we do data regularization and augmentation. Okay, optimizers are here. View full screen mode, and then I go there. Okay, is there any questions, or should we go ahead? I'll give you a second to answer. Okay, very good. Yeah, so remember, next week is the final presentation, please, guys. Don't try to rush your job. Don't try to rush the job. I know that that's the style in which you like to do things, but as I said, I try to make the challenge compelling. So if you rush it, I'm not too happy about it. Let's put it that way. Okay, very good. So we discussed last time, remember that we discussed backprop, and we discussed SGD, and we said, oh, you need to have, you need to choose the learning rate right, so that you don't move too quickly toward the local minimum, and you have the chance to move, get unstuck. But of course, that's a very simple procedure. You can try to do something better by some simple tricks that are enough to drastically improve the performance. Okay, that's why in the challenge you also have Adam optimizers, so you can experiment with Adam optimizers. Okay, so challenge optimization are, as we said, right? So we want to arrive to the global optimal, but there are many local optimals around, and so we don't want to get stuck there. The issue is that local optimal is the biggest issue for deep neural network. Okay, and so in most neural network, right, there is this idea that if the network is large enough, even the local minima behave pretty well. Okay, so if you find a good local minima, you're happy, and this is something else that you can verify by yourself, right? So you say you take a certain neural network, you train it, you get to an accuracy of 90%. Then you take the same neural network, you change initialization, you end up again with a network that achieves 90% accuracy, and then you compare the two networks, and the weights of the two networks are very, very different. Okay, which means that there is a large parameter space. Okay, in the neural network, in the class of neural networks, and if you start from a random initialization point, you start from from points which are very, very far apart in this initialization space. And when you train the neural network, you get to the closest minimal of the network, and this closest minima still gives you 90% accuracy. Okay. So of course, if you had the resources, you could explore all the optimization space, and you will find the best minima. You will find the global minima, and maybe the global minimal accuracy will be 92%. So the question becomes: is it reasonable for us to spend all the efforts in order to explore the optimization space and find the minimal optima, when the improvement that we have over a local optima is only of 2%, something of that sort, right? So this is the wisdom of the practitioners in the field. That's why, in general, we say it is not important to find the true global minimum. We just have to find the local minimum which we like. Good. So remember that we can when we do SGD. If we run SGD twice, we're going to get to the curvature of the optimization space, and this is what we call the Hessian. And if you look at the curvature, you see that sometimes we are in a regional space where there's a very high curvature. So what happens is when you train a neural network is that you are in this figure, and you keep oscillating between two different sides of this cone-shaped object, and so the progress slows down because we are bouncing around back and forth. And so yeah, also some cost function that you have no critical points, and so when you do the classification, when you plot the loss as a function of the weights, the loss is very, very smooth. So what happens is that the gradient becomes very small, and when the gradient is small, then you have, let's say, a small signal that you can use for backprop. Okay? So if you have a small gradient that comes from your first derivative in the backprop, so the derivative of the loss function with respect to, let's say, the last layer of the network, then the activation function will tend to diminish the magnitude of this gradient, so that there is this phenomena that it's called the vanishing gradients, meaning that when you start backpropagation from the bottom of the network, the gradient is a certain magnitude, and as you move up toward the different layers, then the magnitude of the gradient diminishes. And if the gradient, the magnitude of the gradient diminishes, then you understand that the network is evolving too slowly. So that's why sometimes people do gradient clipping, meaning that if the gradient is too large, then you clip its magnitude, and if it's too small, then you renormalize it to have a magnitude of 1. Okay, so you can keep the gradient magnitude alive. And another phenomenon that happens is that you hit very close to an activation function. So now the gradient is very, very large. So now as you go up toward the layers, then actually the gradient magnitude explodes. So you have the different problem in which the gradient increases drastically, exponentially from one layer to the next. And so in that case, you have to do the opposite, and instead of renormalizing the gradient magnitude to 1, you have to clip the gradient magnitude and renormalize to 1 to avoid numbers which are too large. Now you're going to tell me, oh, well, Stefano, which one is it? Either the network has vanishing gradients or the network has exploding gradients. How is it possible that you're telling me that we are doing the same procedure and we have two different problems in which one is the gradients are too small or the gradients are too large? Which one is it? The answer is that you always have either one problem or the other problem, meaning that you can imagine that there is a certain equilibrium, right, in which you can train the network, and this equilibrium will be corresponding to the optimal, let's say, to the optimal choice of hyperparameter, let's say learning rate, let's say temperature of your activation function, whatever, and that's the optimal training. If you go in one direction, then the gradient vanishes. If you go in the other direction, the gradient explodes, and that's why people have to explore the optimization parameters so that you can find the balance point in which your gradient is just the right magnitude. Okay, so remember, if somebody gives you a network and the network it's as a gradient which is exploding. Then you have to tweak the network, change the parameters of the network of your settings so that now when you train the network, the gradient vanishes, and now you revert some of the changes, and now the gradient is exploding, and you go back and forth until you find the regime in which the network is training optimally. Okay. Yeah, so this is what we were saying. So the idea is that now we can discuss some possible techniques that tend to keep you on this path of having a gradient magnitude which is neither vanishing nor exploding. And one of the techniques that we use is momentum. Okay, so if you see that the gradient has very large variations from one iteration of SGD to the next, then you know that there is something going wrong. And you know that you're oscillating across these two barriers of the Hessian. And so what you can do is that you can try to enforce more stability in the training. And you do this, you take the average direction, okay? You try to sum up the different SGD components, and you want to take the average of this. But of course, you want to do this as you're calculating the gradients, right? So you want to influence the calculation of the gradient on this type of averaging effect. So what we do is that we do this. We insert some momentum. Okay, we do some averaging of the current gradient with the past gradients. So we implement this averaging as a filter. Okay, as a sort of causal filter. And so we calculate the gradient, and now instead of applying the gradient as it is, we take the past gradient for a fraction of alpha, and we add 1 minus alpha, the new gradient, and then we update the weights of the network with this smoothed out gradient. Okay, so this has the effect of accumulating the direction of the past gradient in the contribution of the network update, so that in a sense you are averaging out the large variation in the gradient calculation which you have in this situation in which you're bouncing back and forth from the two sides. Okay, then sorry, check the time, guys. And then adaptive learning. So what we want to do is that again we are in this regime in which you have two weights. Okay, so this is the first weight of the network. This is the second weight of the network. Of course, this is a conceptual representation, right? So this is in a network with only two weights. You have to abstract this discussion to larger dimension. But let's see what happens. So what happens here is that on the W2, right, we have very large variation, right, from one network to the next. So you see this here, large component, large positive component, large negative component, large negative component, large positive component. So we are moving back and forth a lot. But here, right, we are progressing slowly on the other component, right? So this other component is progressively going always in the same direction forward. Okay, so we should slow down the learning on the parameter 2 and speed up the learning on parameter 1. Okay, so the learning rate should not be applied to the whole learning vector uniformly, but you will want to split some of the parameters that move slowly and some of the parameters that move fast and change the learning rate according to that. Okay, you see, right? So this is, you will slow down this and you speed up this guy, slow down this guy, speed up this guy, slow down this guy, speed up that, and so on and so forth. Okay, so what you do is that you accumulate the square gradients now. So you have this Ri, which is Ri plus Gi square. So this I indicates that this is the entry of the ith entry of the vector. And then when we update each single parameter in the weight update, then we use this Ri, okay, to adjust the contribution. Okay, so the idea is that we speed up on the direction of the very flat gradient and we slow down in the direction of the flat gradient. Now, this is called adagrad. So adaptive gradient becomes adagrad. Of course, the question that you will ask me is, aren't we changing the optimization direction by doing this? The answer is yes. But if people decide to use it, it's because the trick works. Okay, so some of the tricks some of the discussion that we have here, they are, of course, very much tailored to the experience that people have had in the past decades training deep neural network. And so it is true that that we are breaking what is our understanding of optimization theory. But for example, in this case, maybe the different parameters belong to different layers of the network, so that you can imagine that there is some sort of independence that you have the freedom to utilizing when choosing the parameters. Very good. So this is the old gradient descent, and this is the new gradient descent, where you have this Ri parameter accumulates the square of the gradients. Again, we have this idea that we have to check the magnitude of the problem in a certain direction, and then you update each entry to make it we update each entry in the weights according to this R square. And you might notice here that there is a beautiful delta, and this is very much what you will expect, because if the magnitude is 0, then you will have too much sensitivity to the certain gradient. So you have to smooth out this rational function, so that instead of shooting up to infinity, it shoots up to this epsilon over delta. Okay, this is the usual trick, right? So this is how you stabilize a rational function. Let's say that this rational function will have 0 in 0. Sorry, it will go to infinity as 0 if there was no delta. When you put the delta, you're actually capping the vertical magnitude, the vertical extension of this function to epsilon over delta. Okay, so you choose the epsilon over delta so that you have this nice rational function, and you now go to infinity. Okay, very good. So this is the final update rule. It's a sort of weighted average there. And you can also combine a smoothing factor, which is this delta, and again, as the idea of the filtering, the idea of a memory coefficient, so that you don't, so that you can decide how much memory, right, you want to have on this smoothing coefficient. Okay, so does it depend only on the previous gradient, or does it depend on the gradient very much in the past? And this is called exponentially weighted average. And why is it exponential? Because if you explode this across multiple iterations, so this is an I minus 1, okay? Ri is equal to rho times Ri minus 1. So it's, sorry, Ri at t minus 1. So if you explode this, this is an exponentially decaying sequence. Okay, so it's, so let's say that Ri at time 0 will be weighted with rho to the power of t multiplied by the R0. Okay, good. So this when you add this, you do RMS prop. So your RMS is still root mean square, and so it's like Adagrad, but you add this weighting coefficient, and now we get to Adam, which is the optimizer that everybody likes. Okay, if you are training deep neural network, the neural network is misbehaving, then you just use Adam as an optimizer. Adam usually fixes all the problems that one has. So if the network is still not training, you have other type of problems that are beyond the optimizer. So remember, Adam is our favorite optimizer. And what do? We combine RMS prop with momentum. Okay, so we said the momentum takes the gradient and smooths out the gradient direction using this rho. And then we said that RMS prop takes each entry of the gradient and considers the speed at which this gradient has been updating and try to balance it out. And this is with this GI square. So if you put it all together, then you will get that the omega I is equal to the omega I minus delta epsilon over delta. Okay, nu I, and we have plus square root of I at the denominator. Okay, so this is the usual trickery that we use when we train deep neural networks. Then so you can have a bias correction where you have this, right? So we don't need to discuss this too much in detail, but you can understand that this has not a zero mean It's not a unitary mean function. So if you want to normalize to the one mean, then you use this normalization factor. And here you see the exponential nature of this correction. Doesn't matter. Okay, good. Let's do another 5 more minutes. Another set of slides on regularization, and then we move forward. Okay, so let's go this view full screen. Let me check that everything was fine. We go to full screen. Okay, we starting. Okay, regularization. So what do we call regularization? Regularization is any modification that we make to a learning algorithm that is intended to reduce its generalization error, but not its training error. Very good, very nice. We have to understand what is a generalization error and a training error, but apart from that, we're all good. Okay. So remember that we did we had this set of slides in which we were fitting a deep neural network to this function, which is x sin x. Okay. So what you can do next is that you can add some noise to the sampling point. Okay. And then you can train the network again. And you can see what is the effect of the training. Okay. Now, why we do this, it's clear, right? Because in a sense, adding noise, it's something that would be occurring in all sorts of data sets. So when you observe data, you always observe data plus noise. This is the nature of existence. Okay, we live in a world that is always adding noise to whatever we measure. Okay, this is the uncertainty principle, right? So this is a reality that it's baked into our universe by quantum principle, even, right? So you cannot imagine that you will be able to collect data without error. Okay, so the question then becomes, since we know that we have data plus error, we have to express what is our desirable objective, not in terms of reproducing the data set exactly, okay, but sort of capturing what is the underlying pattern in the data. And this is where we cannot be any more precise regarding this notion, because our understanding of the nature of noise is very limited in general. But in this case here that we have, we can idealize the situation as follows. We know that the underlying pattern of the data is x sin x. We can simulate that in the acquisition procedure, we obtain y plus some noise. Okay, we obtain y, which is equal to the true x sin x plus some noise. Okay, and then we can ask ourselves, if we train a deep neural network, can we have a deep neural network that captures the x sin x and rejects the noise? Okay, the deep neural network, is it able to learn the pattern of the data, which is x sin x, and then disregard, right, learn that the perturbation produced by the noise are not relevant? Of course, this is something very difficult to express in a general setting, but in this setting we can do it. So what are we going to do here? We're going to take a network and train the network on the data plus noise. If we do this, you see that the network, in this specific case, it's jumping a lot back and forth in order to capture the noise. And this makes us unhappy because, of course, we're not capturing the pattern of the data. So we can ask ourselves, why is this happening? Of course, it's possible that the network has too many parameters, so we are overfitting the data. It's possible that we have to choose multiple reinitialization, so that the way in which we do train and test, it's averaged, right? So we can choose across multiple initialization and multiple train test split. The network gives us the smoothest performance. But another trick that we have in our hands to do this is regularization. So we're going to see this next. And what is the idea? The idea is that the behavior of the network is unwanted because it's not smooth, right? The network is changing a lot as a perturbation in the input occurs. You see here that basically, if we change our x to be a certain x plus epsilon, then the output of the network changes a lot. And in the mathematics of the neural network, why does this happen? This happens because the magnitude of the coefficients is large. So if you want to improve the situation from where we are, what we can do is just to reduce the magnitude of the coefficients of the network. Very easy. Okay. So what do? We take our loss function and we add a penalty, okay, that penalizes large weight magnitude. Of course, what do we mean by magnitude can be measured in different ways. We can take an L2 regularization where we take the magnitude square, right, the square, or an L1 regularization that takes power 1. Of course, you understand the curvature of these norms changes, right? So as the norm increases, deviating away from the exact, from the zero value gets penalized more and more, okay? It gets penalized exponentially more. So L1 doesn't penalize large weights, L2 penalizes large weights more, and then as you increase the magnitude, you're clamping down, you're introducing larger penalties from the variation from zero. So, and what is the effect of this? Is that the effect of this is that we do actually, when we do backpropagation, what happens is that we add the constant term, right, which corresponds to the past weight. So it's as if we are adding a momentum to our weights, right? We're adding an averaging out of the current update with the past update. And so if we add this regularization, we see that when we train the network, then the network learns to be smooth, right? Meaning that the coefficients are small, so the changes from a small change in x are being dampened, and so everything becomes nicer. Okay, very good. Early stopping. When you do training, you will often see this plot. Okay, so in blue we have the training loss, and in orange we have the validation loss. And what will happen in all of your experiments, you will see that the training loss is always going down, and then you will see that the validation loss goes down for a certain amount and then shoots up to be large again. And which phenomena is this capturing? Is capturing this following phenomena. The network has a lot of parameters, as we said. The network is a lot of space, let's say, in its neuron to store information. Okay, so as the training keeps going, what the network starts doing is starts memorizing the entries of the data set. Okay, so the network learns that in order to reduce the loss, it has to correctly classify all the images, and some images can generalize well, some other images it cannot generalize well, and the images that you cannot generalize, you just memorize them. Okay, so since the network has so many parameters, then there is space to memorize a specific label of a specific sample. And how do we know that the network starts memorizing? Because we train we test the network over a set of unseen data, and for this unseen data, then the loss is no longer decreasing uniformly, because then on the unseen data, the memorization will give a wrong label. Okay, so that's why we sacrifice some of the part of the data to do validation. Okay, so if we want to take a decision on whether we have passed the point in which the network learns generalization, and we are now in the regime in which the network is memorizing, we will need to use some data to know if this has happened. We are not going to use the training data. We're not going to use the test data, because the test data is holy for us. Okay, the test data is there only for us to show to a possible client, to a person that is asking us to do a certain job, that really the performance of the network is as claimed. Okay, this guy can come and is going to ask us, do you guys really did a good job? He says, oh, look at this data. The network has never seen this data, and the network, even by not knowing what's inside this data, is going to have this performance. So the training data is untouchable. Yeah, sorry, the test data is untouchable. So the only choice that we have is to take the training data and to chop off some of the training data and to use it to see if we are at this point. Okay, so in a sense, right, the fuel of the training is always the training data. So if you want to do anything in training which goes beyond SGD, then the only way in which you can achieve this is by paying a price in terms of training data. So if you want to do a better job, then you have to collect more data. Okay, so the idea here is as follows. We have 80% of the data set which is training data. We're going to take away a small portion of this. We're going to take 10% of this, and we're going to use this at each iteration to check what is the performance of the training data over this data, which we call a validation data. Okay, and then as soon as we see that the performance of validation data is starting to decrease, then we stop the network. Okay, and this is what we call patience. Okay, patience is defined as the number of epochs to wait before we do early stopping. So we check the validation data, we see if the performance has improved, yes or no. If it has not improved, then we consume one of our patients. And patience is always set between 10 and 100, depending on how big is the network. And then we see that if the network is not improving the performance of the validation data for more than 10 epochs, then we do early stopping. Okay? Because we know that we are just memorizing. Very good. So you can imagine if you're training a very, very large neural network, getting to 500 epochs could take you a week. So early stopping is very much relevant. But again, in order to do it, we have to consume training data. Very good. Next slide. Next slide. Let's share. Share. View. Where is full screen? Where is full screen? Not showing up. No, full screen. Okay, good. The sharing failed, so we have to redo it. Let's try again. Full screen. No, the sharing failed. Let me try to share again. Stop sharing. Mysteries of Adobe. Adobe makes too much money with this product, so they have no incentive of improving their product, right? So the company is doing very poorly because they have had very, very small investment in AI, even if they make like a couple of $1 billion a year. So hopefully we're gonna see the ending of this company. Okay, very good. Now data augmentation, that's what we already discussed, right? For the challenge. So take an image, you do the rotation. So we're discussing data augmentation for MNIST. MNIST is a black and white image. So some of the things that we could do with MNIST can do with regular images, and then we can do some more stuff if we have color images. For example, what we discussed is crop and pen, rotate. But if you have a color image, you can also have a change in hue, saturation, illumination. You can do different transformation. And as we said, data augmentation is already there in the data. So there is already a package in Python or in PyTorch, wherever you look for it, that does the data augmentation, so you don't have to worry about it. And this is what we're discussing, right? Be careful that once you do data augmentation with MNIST, you have to choose the range of the data augmentation that is meaningful. For example, if you rotate a 6 of 180 degrees, then it's going to become a 9. So don't augment your data so that you collapse the two labels. And the other important thing is dropout. I didn't put it in this challenge because I didn't want to make it too long. But basically, you have to experiment with dropout yourself. The idea is as follows. That when overfitting occurs, the model becomes too sensitive to slight variation on the input and start fitting noise instead of the true pattern in the data. So when you do L1 and L2 regularization, you shrink the weights to avoid this problem. But the trick is that if you have a very deep network, even with very small weights, there can be a certain correlation in the behavior of the nodes and the neurons across different layers, so that you are still fitting the data. Okay, so the network is very smart, and even if you curb the amplitude of the weights, the network can learn to coordinate the output of certain neurons so that the output is still fitting the noise. So this is called co-adaptation, okay? And so the network is smarter than you, and basically is defeating your regularization, okay, whether L1 or L2. So what do people do? They try to trick the network, and they try to avoid the network operating across layers, and they do so by doing this. You stick with you start with a standard neural network, and then you randomly deactivate a subset of neurons at each iteration. Okay, so this is the large network. And then in one instance of training, you randomly deactivate some of the neurons. So now we have this other pattern. And then you apply SGD to only this subset of the neurons. Another round comes, and another random set of neurons gets deactivated. Okay. More formally, you take the neurons and you form a binary mask mu, which is independent from everything else, and then you train the network for this subset, and then you update the weight for this subset, and then you average the full network with this subset. Okay. And so all we need to do in order to do dropout is to decide with which probability they're going to be active. And the input nodes, let's say we fix the probability to 0.8, and the hidden nodes we fix the probability to 0.5, and we are all happy. And dropout works. It's really, really effective. And what you can do is also it's for saying this, right? So this is, I guess this is CIFAR 10, right? And if you do dropout, you really improve the performance substantially. Now, if we had to look at dropout, we can ask ourselves, do we have another name for this? And the other names that we have for this is ensemble method. So in a sense, is as if, right, each subnetwork that we have, it's sampled, right? And then at the end, the output that we provide, it's an average of all the different subnetworks that we are training. Okay, so it's as if we have, instead of having one big network with a random mask, we have, let's say, 10 different subnetworks, and then we train each subnetwork separately, and then we take the average of the outputs, and we said that the average of the output is the final decision that we have. But the idea is that if we really had to implement this method explicitly by having 10 different networks that are active at each time, this will consume too much resources. Okay, this will require a lot of hardware. This will require a lot of computation time. This will require a lot of processing time. So in a sense, dropout takes out this process, right? It emulates this process by simply by simply using the same architecture and implicitly having the averaging of these experts across the network, because then when you do inference, you forget about the dropout. You use the network as if dropout was never applied, and then there is no increasing complexity what you were doing during let's say the regular operation where you didn't apply dropout. Okay, very good. So the training time, a neuron is present with a certain probability, but at test time, the neuron is always on. Okay, and there is this idea that there is some sort of natural aggregation that happens at the activation function, and this aggregation emulates having multiple networks. Very good. Okay, that's it. I think we are very much in time today, so let's take. We are 8 exactly. We are on the hour, so let's take a 3 minutes break. We go walk around, and then we have the movie presentation, and then we move on with our life. And please, guys, we need a volunteer for the next movie, and then we need to choose the next movie. Otherwise, I'm going to be unhappy. Okay, I'll see you back in 2 minutes. Prepare, please, the presentation on the movie. Okay, go ahead. Okay, guys, I think we have a movie presentation, correct? Guys? We have a movie presentation, right? Let's see if the student is back. Maybe the student is not back yet. Who was the student in charge? Who was the student in charge of it, right? Who was the student in charge? Let me ping the student. Do we have a student in charge of this? Hello. My own voice. Yeah. Didn't we have a student in charge of the student presentation, guys? Am I dreaming? Okay. Maybe we'll do it next time. Okay, we'll do it next. I think there was a student on the basic. No worries. We'll do it next time. Otherwise, we find another volunteer. Okay. Let me just double check. Chen, okay. Okay, guys, I guess we have no movie presentation this week. No, I really want to somebody tell me about that movie. Okay, no worries. Then we start the recording now so that we can talk a little bit more. We say hi to the guy on YouTube. Okay.